Welcome to lesson 35 in power system analysis. In this lesson, we will continue our discussion on power system stability. Till now, we have talked about the basic problem of power system stability. Then we tried to classify the stability problem into different types, and we started with the most important one, that is the rotor angle stability problem, and we developed the dynamic equation for rotor angle dynamics of a synchronous machine. Then we went into the single machine infinite bus problem, and we developed this swing equation for this kind of a system, including the damping term in the system. In this lesson, we will continue the discussion. We will start with the small signal stability, that is when the disturbance to the system is much smaller. Then we have seen that power system swing equation that governs the dynamics of the rotor angle is a nonlinear differential equation, but when we are talking about the small signal disturbances, then we can think of linearizing the system and use this linear system analysis for this. So, we will start this lesson with the problem of small signal stability and how to analyze small signal stability for a single machine infinite bus system. We will take up some examples to illustrate how we do this. Well, on the completion of this lesson, you should be able to explain the concept of small signal stability, develop the mathematical model for small signal stability, and analyze small signal stability for single machine infinite bus system. Well, as we said, we will start this lesson with small signal stability problem. That is what we are considering here. Is the system is running under normal operating condition with all the variables being stable, that is having constant values. Now, there is a disturbance which takes place. This disturbance is not of very large magnitude, but a small magnitude, but this is going to perturb the system variables, and these perturbations, because the disturbance is small, are going to be small perturbations. Therefore, we know that the dynamic equation of power system is nonlinear. That is, if we see the swing equation, we have the swing equation as m d2 delta by dt2 plus d delta by dt is equal to Pm minus Pe, and Pe term, as we had seen, is a term which is a nonlinear term. It is a function of delta, and in fact for cylindrical rotor machine, the value of this Pe is equal to P max sine delta. So, this equation is a nonlinear equation, but at the operating point, normal operation where it is taking place before the disturbance, if the disturbance is small, we can linearize this dynamic equation about that point and study the perturbation as a linear system analysis. This is what we do when we try to study the small signal stability for power system. So, let us start with this swing equation that we have. M we write as h by pi f, where h is the inertia constant in per unit, and we have P is equal to Ev by x d sine delta, which we call as P max sine delta. Now, here we have seen this Pe being nonlinear. So, if we are talking for small signal stability, we will have to linearize this dynamic equation, which is a nonlinear equation, about the operating point. So, for small disturbances, the swing equation can be linearized about the initial operating point, that is at delta is equal to delta 0, and we take a small perturbation of delta delta. So, what we are saying is we are linearizing this expression for the dynamics of the synchronous machine about the operating point delta 0, and we are considering small perturbations, that is the change in delta is small, delta delta is small, and therefore, we will use the linear relationship. So, let us see how we linearize this swing equation for the synchronous machine. So, now again writing the same expression, m d2 delta by dt2 plus dd delta by dt is equal to p m minus p e, which is a function of delta. Now, we say that delta is being perturbed by a small amount from delta 0. So, we can write this delta as delta 0 plus delta delta. So, replacing this delta by delta 0 plus delta delta, in this expression we get m d2 delta 0 plus delta delta by dt2 plus d delta 0 plus delta delta by dt is equal to Pm minus Pmax sine delta 0 plus delta delta, that is we have replaced all delta by delta 0 plus delta delta. Now, we can write Pmax sine delta 0 plus delta delta as, that is we expand this term, then we get Pmax sine delta 0 cos delta delta plus cos delta 0 sine delta delta. Now, since delta delta is small, so sine delta delta will be very much equal to delta delta in radians, and cos delta delta will be very nearly equal to 1. So, substituting these values, we will get m d2 delta 0 by dt2 plus m d2 delta delta by dt2 plus d delta 0 by dt plus d delta delta by dt is equal to Pm minus Pmax sine delta 0 plus Pmax cos delta 0 into delta delta. That is, we have substituted for this as delta delta, and cos delta delta is equal to 1. So, substituting that, we will get this. Now, here m d2 delta 0 by dt2 plus d delta 0 by dt is equal to Pm minus Pmax sine delta 0, because initially the system is operating in a steady state before this disturbance took place. So, the relationship at delta 0 was holding good like this, that is m d2 delta 0 by dt2 plus d delta 0 by dt is equal to Pm minus Pmax sine delta 0. So, removing this term away, we will get this as m d2 delta delta by dt2 plus d delta delta by dt is equal to Pmax cos delta 0 into delta delta. So, this is the expression or the linearized expression for the swing equation, that is the dynamics linearized equation for the dynamics of the synchronous machine or the rotor dynamics of the system. So, we normally write this Pmax cos delta 0. Actually, what is this Pmax cos delta 0? If we see this expression, Pe is equal to Pmax sine delta 0, and if we differentiate this, then we will get this as Pmax cos delta. So, basically this expression that we have got, that is del P by del delta, will be equal to Pmax cos delta. So, at this is basically giving us the slope of the power angle characteristics of the machine about the operating point delta 0, and we call this as the psi, that is d Pe at delta 0 by dt. This is the slope of this power angle curve of the synchronous machine at delta 0 we are denoting it by psi, and we call this as the synchronizing coefficient of the synchronous machine, or it is also called the stiffness coefficient of the machine. It is basically the slope of the power angle characteristics at the operating point delta 0. Therefore, now we are writing this expression as m d2 delta delta by dt2 plus d delta by dt plus psi is equal to 0. That is, we will take this term, that is, what we are saying is we are writing the characteristic equation for this relationship. So, we will write this as m d2 delta d2 delta delta by dt2 plus d delta by dt plus psi is equal to 0. Now, this expression, I am sorry, here we had missed this term delta delta. So, finally, what we get is, I am sorry, here we had missed this expression delta delta. So, finally, what we are getting is basically this m d2 delta delta by dt2 plus d delta delta by dt plus psi delta delta is equal to 0, describes the dynamics of the single machine connected to infinite bus system for small disturbances about any arbitrary operating point, that is, the operating point wherever we want, that delta 0. About that delta 0, this is describing the dynamics of a single machine connected to infinite bus system, that is, the dynamics of the single machine about the arbitrary or any starting operating point. Dynamics of this system can be analyzed by finding the roots of the characteristic polynomial, that is, this is a second order polynomial that we have, writing d2, that is second derivative, as s, that is taking the Laplace transform, we will get m s square delta delta plus ds delta delta plus psi delta delta is equal to 0. So, writing the characteristic polynomial, we will get m s square plus ds plus psi is equal to 0, and we can find out the roots of this polynomial, which will tell us about the dynamics of the system. This is how we analyze the dynamics of a linear system. So, looking at this, the roots of the characteristic polynomial m s square plus ds plus psi is equal to 0 are given by, there will be, this is a second order equation. So, there are going to be two roots, and we will get the roots as s1 and s2. This will be equal to minus d plus minus square root of d square minus 4 m psi divided by 2m. This is a quadratic equation, so we know how to find out the roots. So, the two roots are given by this relationship. For normal operating condition, normally what we have is m psi is much larger than d square. The damping terms are normally much smaller, and therefore, we will get this term as S12, that is the two roots, as alpha plus minus j omega, where alpha is generally less than 0, that is, alpha is negative, and omega, which gives the frequency of oscillation, is given by root over psi by m. So, with d small, that is for lightly damped system, delta is equal to delta plus delta delta, which will be finally leading to the same delta 0. That is, what we are trying to say is, if the system is operating initially at delta 0, we somehow give a perturbation to the system, that is, we make a delta delta change in the rotor angle of the system suddenly, then what happens is the system will go through a dynamics and will finally settle down again to delta 0, that is, the dynamics will slowly be damped down and it will go back to the same stable operating condition with the rotor angle as delta 0. However, if either psi or d, any one of them is negative, then what we get is that the value of alpha becomes positive, and the meaning of this is that the oscillations will build up and the system will go into a runaway situation, that is, this machine delta angle will keep on increasing and it will be a runaway situation. This means that the generator will lose synchronism from the system. So, this is what we normally get, and therefore, basically when we are trying to analyze the small signal stability for the system, what we are looking at is whether due to small perturbations about its operating point, the system is going to come back to the same operating point or it is going to run away. That is, whether the oscillations get damped out or these oscillations will build up and the system will get desynchronized from the rest. That is, the machine will get desynchronized from the rest of the system. Now, let us see this same situation. Here we have this curve which is shown here is the curve which is showing this P e is equal to E dash V infinity by x t sine delta. This is the term that we get for a cylindrical rotor machine. That is, this is the power angle characteristics for the cylindrical rotor machine in the generating mode like this, and in the motoring mode it will be like this. I am sorry, this should go beyond this. This curve is not very proper. For generating mode it is okay. It is like this curve is like this, and for salient pole machine the electrical power output is given by this relationship, where we find this is the term which is same for the cylindrical rotor machine, but this is a term which is added which is having sine 2 delta term involved, which means it is a second harmonic term, and this is shown here. So, this term, that is the second term in this, is shown here, and finally for the salient pole machine the power angle characteristics will be the sum of these two terms. So, it is given by this line here. Now, what we find is that the salient pole machine has a little more maximum power available than the cylindrical rotor machine. This happens because of the reluctance term or the second harmonic term here, which we normally call as the reluctance term, because it is the reluctance power. This term is coming mainly because of the saliency of the synchronous machine poles. That is, what we are seeing is that the reluctance in the direct axis and the quadrature axis are not same, and because of that only this term is coming, and that is why we call this as the reluctance term. And in fact, there are machines which are built based on this reluctance power or reluctance torque, which are called reluctance motors themselves. Anyway, so we have these two characteristics, and what we see from these characteristics at any operating point, let us take this point on either of the cylindrical or rotor machine or on salient pole machine. Let us start with the cylindrical rotor machine. Suppose we are operating at this point. Now, at this point we have angle delta 0, and what we find is that the slope here which is the synchronizing coefficient, is positive here. Now, suppose we slowly keep on increasing the power output of the machine, that is, we very slowly increase the mechanical input to the machine. What is going to happen? Because of that, the delta angle will keep on increasing. So, it will start from here, say initially it is starting here. So, we will keep on increasing very gradually. So, machine operating point will keep on moving, that is, delta angle will keep on increasing. Since we are increasing the mechanical input and electrical power output is also increasing because of the increase in delta angle, therefore, these are all the time getting matched and the machine is running in synchronous condition, that is, the machine speed remains synchronous. We keep on doing this till we reach this point. Now, suppose if we increase the mechanical input by a very small amount at this point, what will happen? Delta angle will again increase from here, that is, at what is going to happen because of this increase of delta angle? Now, delta angle has crossed 90 degrees and what is happening? The electrical output of the machine is going to reduce. The mechanical input has been increased, whereas the electrical output has reduced, which means there is going to be a difference between these two powers. So, there is going to be some acceleration which will take place, and because of this acceleration, what happens? Delta angle will keep increasing. So, delta angle increases, then further the power output of the machine, electrical power output of the machine will decrease, and this will continue like this, and the system will lose synchronism, because the speed will keep on increasing even if we have not increased the mechanical power beyond this value. So, this point is what we can get is the maximum power output from the machine. We cannot get any more power output from the machine even if we work the machine very gradually. So, we call this point as the maximum power output, or P max, and we also call this point as the steady state stability limit. That is, the machine will lose its stability if we try to operate this beyond this point. So, if we want to work the machine beyond this maximum power, the machine loses stability, and we have worked this very gradually. So, we have assumed that there is no dynamics or transient taking place, and the system is all the time working in steady state, and that is why we call this as steady state stability limit. Same thing can be seen for the salient pole machine. Here also we will get a P max value, and this is the value which we call the steady state stability limit. And what we find that as we keep moving on this power angle characteristics, the synchronizing coefficient, that is the slope, is positive up to the P max value, that is up to the steady state stability limit. At steady state stability limit, the value of the synchronizing coefficient is 0, that is the slope at this point, slope of P del P by del delta is 0 at this point, that is the stability limit point, and beyond this point the slope becomes negative. That is what we said, that if either of these, that is, if we get either psi value, that is this value psi becomes negative, then we get alpha as positive, which means the system is going to become unstable. That is, the roots come in the right half of the S plane, which shows instability, because the dynamics, the oscillations in this case are going to build up. And this is what we have seen here, that that if we psi becomes negative, that is we try to operate in this region, then we lose synchronism, because any small change in PM where we would like to raise the output, in fact when we change PM by a small amount, increase it, then delta angle increases, but PE reduces, which means the difference increases and the rotor will keep on accelerating. So, therefore, the speed will keep on increasing and it will lose synchronism. So, this is how we understand the steady state stability of the system, that is with very gradual changes. If we work, then we call this kind of a stability, that is the maximum allowable power from a machine to the system, is what we call as the steady state stability limit. That is, beyond that point the stability of the system even under steady state operating condition is lost. Anyway, we are talking mostly about small signal analysis, where we are saying that the effect, what is the effect of damping and what is the effect of synchronizing coefficient. We have seen synchronizing coefficient or the stiffness coefficient, if it becomes negative, the system loses stability anyway. Also, one thing which we can see from these characteristics is the slope for the salient pole machine is larger than the slope for the cylindrical rotor machine in the normal operating region, that is in the stable operating region. That is, what we see is that the salient pole machines are more stiff and the change in their delta angle for a given increase in power output is much less compared to that of the cylindrical rotor machine. Another thing that we see normally is that the maximum power point for a salient pole machine is reached below 90 degrees, whereas for a cylindrical rotor machine this maximum power is reached at 90 degrees, that is when sin delta becomes equal to 1. So, this is about the steady state stability part, where that is where we are talking about the dynamics when we move at very small rate from one steady point to another steady point, very gradual changes taking place, where we are considering no dynamics building up. Let us go back to the small disturbances. So, writing the linearized swing equation, m d2 delta by dt2 plus d delta by dt plus psi delta delta. We are replacing m by h by pi f as we had seen earlier, that is writing instead of m, that is angular momentum, we write in terms of inertia constant. Now, this expression can be written in a standard form like this, that is d2 delta delta by dt2 plus twice zeta omega n d delta delta by dt plus omega n square delta delta is equal to 0. This is a standard form of second order differential equation for analyzing the dynamics of linear system. Now, if we write this expression in this form, then we will get omega n is equal to square root of pi f0 by h into psi, and zeta will be equal to d by 2 square root of pi f0 by h psi, where f0 is the synchronous frequency of the system and d of course is the damping coefficient. Now, damped frequency of oscillation for this particular system is given by omega d, which is equal to omega n square root of 1 minus zeta square. I am not going into the details of how to get all these values. One can go through any standard book on control system to understand that. What we are saying is only we are putting the results here. So, the damped frequency of oscillation omega d is given by omega n into root over 1 minus zeta square, and for small perturbations delta 0 about the initial operating point delta 0, the dynamic response of the system, that is, if we give a very small perturbation equal to delta 0 at the starting point delta 0, that is, suddenly we change the delta angle at time t is equal to 0 from delta 0 to delta 0 plus delta 0, then how this change in angle is going to take place is what we are writing here, that is the solution for the dynamic equation, linear dynamic equation that we had can be written in this form, that is delta at any time t, the change in the angle from delta 0 is equal to delta 0 divided by root over 1 minus zeta square e to the power minus zeta omega n t into sine omega d into t plus theta. Now, this is giving us the change in delta from delta 0. Similarly, the change in frequency, that is delta omega from omega 0, is given by minus omega n into delta 0 divided by root over 1 minus zeta square e to the power minus zeta omega n t into sine omega d t, and the delta at any time t for t greater than 0 is given by delta 0 plus delta, where delta is given by this relationship, and omega, that is frequency at any time t at t greater than 0, is given by omega 0 plus delta omega, and the time constant for this oscillation is given by 1 by zeta omega n, which is equal to twice h by pi f d. So, these are the results which I have put here, that is how these dynamics are seen when we give this small perturbation to the system. I am showing this on this diagram, that is, we started at this delta 0 at t is equal to 0, we have given a perturbation of delta 0, then the system will go through a dynamics like this. If we have the damping coefficient d which is positive, that is, what we are seeing is the system goes through oscillation, but these oscillations are slowly dying out, and finally the system will reach a time after some time the angle delta 0 again. But if the value of d, the synchronizing the damping coefficient, is negative, then we go through this curve. We go through this second curve where we find that these oscillations are gradually building up, and the system will finally lose synchronism, because delta angle will keep on going higher and higher, and after some time it will be a runaway situation. Now, let us try to see this through some example. So, we take a very simple example. We have a 50 hertz synchronous generator having inertia constant H is equal to 5 megajoules per MVA, and a transient reactance x d dash is equal to 0.2 per unit. It is connected to an infinite bus through a purely reactive circuit as shown in figure. That is, it is connected through a transformer and a double circuit line to the infinite bus system. The reactance values are marked on the diagram. That is, transformer has a reactance of 0.1 per unit. The line, each circuit, has a reactance of 0.4 per unit. The generator is delivering real power of A 0.6 per unit and B at 2 per unit at 0.8 power factor lagging. That is what we are trying to do, is to trying to analyze the dynamics of the system for two conditions. One, when the system initial operating point is 0.6 per unit, that is the electrical output from the generator in steady state is 0.6 per unit, and the second condition when we have the initial operating point where the generator is delivering 2 per unit power. So, and for both these we have assumed that the power factor is 0.8 lagging. So, this is, and the infinite bus voltage is infinity, V infinity is 1 per unit. The damping coefficient in both these cases are assumed to be 0.15 per unit. So, first what we will do is the transfer reactance between the generated voltage and an infinite bus, that is the voltage behind the reactance for this machine. As we have seen earlier, the simplified model had a voltage behind the transient reactance, and so for this voltage source, what is the transfer reactance up to the infinite bus, that is 0.2 plus 0.1 plus 0.42 of these 0.4 in parallel. So, this is the reactance 0.2 plus 0.1 plus 0.4 by 2, that is 0.5 per unit. So, the reactance is 0.5 per unit, and we have the apparent power in per unit as S is equal to 0.6 by 0.8. In fact, this, since we are writing reactance, I have not written J here, otherwise you can write this J because the angle of this is always 90 degrees, it is a inductance. So, S is equal to 0.6 by 0.8, 0.6 is the power per unit and 0.8 is the power factor. So, 0.6 by 0.8 into cos inverse 0.8, the angle will be that. So, the apparent power in per unit can be written as 0.75 with an angle of 36.87. I am sorry, yeah, 36.87, and the current for this I will be equal to S conjugate by V conjugate, because we have S is equal to V I conjugate. So, S conjugate is V conjugate I, therefore, I is equal to 0.75 with an angle of minus 36.87, because S is with an angle 36.87. So, when we are taking conjugate, this becomes minus divided by V conjugate, this is 1 angle 0. So, 1 minus 0 is same as 0. So, the current is 0.75 angle minus 36.87. So, this is the value of current in per unit that we get, and from this current we can now find out the voltage behind the transient reactance for the machine, because the voltage at the infinite bus is given as 1 angle 0. So, E dash, the voltage behind the transient reactance, is equal to V plus J X into I, where X is the transfer reactance between the voltage behind transient reactance to the infinite bus. So, E dash is equal to V plus J X I, this is equal to 1 angle 0 plus J 0.5 into I is 0.75 into with an angle of minus 36.87. This, when we solve this, this comes out to be 1.225 plus J 0.3, that is equal to 1.261 with an angle 13.76 degrees, that is delta 0 is 13.760. So, initial operating power angle is 13.76 degrees, and the synchronizing power coefficient at this operating point psi is equal to P max cos delta 0. So, this will be equal to 1.261 into 1, this is E, this is V divided by x into cos of angle delta 0. So, this comes out to be 2.449. So, synchronizing coefficient at this operating point is equal to 2.449. The undamped angular frequency or natural frequency of oscillation and the damping ratio, that is omega n and zeta, we can calculate as we had seen from these expressions earlier. Omega n is given by this and zeta is given by this expression. So, simply substituting the values here, omega n is equal to square root of pi f 0 by h into psi. So, pi into 50 by 5 into 2.449, this is psi value that we have calculated. So, it comes out to be 8.771 radians per second, and zeta is equal to d by 2 square root of pi f 0 by h psi. This is equal to 0.15 by 2. This is the value of d that we have said we are using. Square root of pi into 50 divided by 5 h value into psi 2.449. So, this comes out to be 0.2686. So, the damping coefficient is 0.2686. Now, the linearized force free equation, which determines the mode of oscillation as we had seen earlier, is given by this relationship d2 delta delta by dt2 plus twice zeta omega n d delta delta by dt plus omega n square delta delta. This is equal to 0. So, this is the expression that we have. Now, substituting the values of zeta omega n in this expression, we will get the expression for the machine connected to infinite bus at the initial operating point, that is delta 0 is equal to 17.36 degrees. Then we get this expression as d2 delta delta by dt2 plus 4.71 twice zeta omega n value into d delta delta by dt plus omega n square, which is 76.93, that is omega n we had seen here and zeta we have seen here. So, substituting these values, we will get 76.93 delta delta. This is equal to 0. The damped angular frequency omega d, as we have seen, is given by omega n square root of 1 minus zeta square. This comes out to be 8.448 radians per second, and the frequency of the damped oscillation f d is equal to omega d by twice pi, because omega is twice pi f. So, this comes out to be 1.345 hertz. That is the frequency of oscillation for this system is 1.345 hertz. This is over and above the 50 hertz synchronous frequency that we have for the system. That is, if we look at this diagram, then we are saying the frequency of oscillation for this system is 1.345 hertz. This is a normal thing that we see, that is the damped frequency of oscillation for the dynamics of the system is normally of the order of 1 hertz or so. So, in this sense, that is why when we are trying to analyze this system, we normally take a time period of a few seconds, because the frequency of oscillation is 1 hertz. So, you get one cycle in 1 second or so. So, when you are doing it for 3-4 seconds, you have got the dynamics for 3-4 cycles. Also, the other thing is, we can say that the time period for oscillation is given by 1 by zeta omega n, that is, sorry, we have seen here time constant is 1 by zeta omega n, and normally around 4 time constants you will find the system would have settled down to less than 1% the magnitude of oscillation. So, the motion of rotor relative to the synchronous rotating field is delta is equal to delta 0 plus delta delta. This is the expression that we had seen earlier, and we see delta is equal to 13.76. This is the starting point, plus 10.38 e to the power minus 356 t. Now, this is showing as time increases, this term is going to reduce, and that shows that the damping is going to reduce the oscillation magnitude, and after some time, that is normally around 4 time constants, it is going to settle back to delta 0. So, this term as t keeps on increasing will keep on reducing and will reduce to 0 as t tends to infinity, which shows that the system is going to be stable when as t tends to infinity. And the frequency of excursion, that is given by this relationship 50 minus 0.2528 e to the power, again which we are finding as t increases, this frequency will also settle down to 50 hertz. Now, when we have the initial operating point where the power being delivered by the machine is 2 per unit, what happens is we again calculate the apparent power with its angle, and the current we get as 2.5 angle 36.87. In this case, we have assumed that the exciter of the machine is able to make the voltage of the machine go up without any limits, and therefore, what we find is that the voltage behind the transient reactance in this case is going to a very high value, because a very large amount of current is flowing, and because of this the change in delta angle is not really much. But if we would have kept the excitation voltage same as that of 0.6, then we would have found that the delta 0 is very large value. Here we have assumed that it is possible to keep the excitation voltage go up to very high values, and therefore, we are finding voltage behind transient reactance as 2.015 with an angle 29.74 degrees. So, now initial operating point delta 0 is 29.74 degrees. At this, we will get again the synchronizing coefficient psi, which comes out to be equal to 3.5. It has got a different value now, but if we would have used E dash as same value as earlier, that is at the value of 1.261, then we would have got a value of delta 0 in this case, which would have been very large, very small. It would have reduced considerably. The undamped natural frequency, again we can find out for this case, comes out to be 10.48 radians per second, zeta comes out to be 0.2246, and we will get again substituting in this expression the values, the again omega d, the damped natural angular frequency comes out to be 10.212 radians per second, and the frequency of damped oscillation is coming out to be omega d by 2 pi is equal to 1.6253. Now, if we plot the variation in delta angle and frequency when we give a small perturbation of delta angle to the system, then we will get plots as shown here. These can be obtained by looking at these relationships, delta delta given by this relationship and delta omega is given by this relationship. So, we can plot delta with respect to time, and for this particular system we have used delta delta as 10 degrees. So, we have given a perturbation of 10 degrees and we have plotted delta and omega with respect to time, then we will get this characteristics. Now, here we have shown characteristics with P m is equal to 0.6 and for P m is equal to 2, the delta angle varies like this. Similarly, the frequency in the two cases are shown here. We have also shown a third case with P m, that is the starting point being 0.8 per unit. So, initial output is 0.8 per unit. In that case also we can see Now, we see that these plots are very similar. When the initial operating point is somewhat different, then there is a slight variation in frequency and delta angle, that is in terms of their damped natural frequency, which we have already seen, and we see that for positive damping these oscillations finally die out, and after a few seconds we get a steady state operating condition. If we take a case where we have damping which is negative. Now, this damping, negative damping does occur into the system sometimes when we have controllers in the system which have very large gain. So, sometimes this does happen, that is the overall damping of the system becomes negative, and in such cases how the system behaves we can see from this example. So, again we are taking the example where the generator is delivering real power of 0.6 per unit at 0.8 power factor lagging to the infinite bus, and the damping D is minus 0.01 per unit, a very small negative damping. What happens because of this? Again same thing, apparent power we are getting this as 0.75, so, and with an angle 36.87. So, the current is coming out to 0.75 with an angle minus 36.87. The excitation voltage, again the same thing, 1.261 with an angle 13.76 degrees, that is the initial operating point is 13.76 degrees. Now, the synchronizing coefficient in this case is again 2.449, the same as earlier case. Now, here we find that the omega n, the undamped natural frequency, is again coming out to be same as 8.771 radians per second, whereas the damping coefficient has now become negative because D is negative. So, it comes out to be minus 0.179, and because of this negative damping, the substituting the values in the expression for the dynamics of the system, we get d2 delta delta by dt2 minus 0.942. This term has become negative because zeta is negative, d delta delta by dt plus 76.93 delta delta is equal to 0, and the damped angular frequency for this again is 8.769 radians per second, which again gives you a damped frequency of oscillation as 1.396, similar to what we have got earlier. However, when we see this expression for delta angle with time, then we see this as delta is equal to 13.76 plus 10.38 e to the power 0.471 t. Now, this is positive. So, with as t keeps increasing, the second term will keep on increasing. Same thing happens for the frequency term. As t increases, the frequency will keep increasing, which shows that the system is going through a runaway condition, that is its frequency will keep on increasing with time. And if we do the plot, we see how the delta angle oscillations keep building up. Same thing happens with the frequency. So, it will keep building up and the system will be in a runaway situation. So, here we have seen how even for small perturbations the system can be stable or can become unstable when either the damping term is 0 or the synchronizing coefficient when the damping term is negative or the synchronizing coefficient is negative. And we also saw that there is a limit to the power transfer from the machine to the infinite bus or the system, and this limit is what we call the steady state stability limit. So, we cannot work beyond this power transfer value. So, with this we will stop today. In the next lesson we will talk about large signal rotor angle stability, that is where we will talk about what happens to the system dynamics when large disturbances like short circuits occur in the system. With this, we end today, and thank you very much. Welcome to lesson 36 on power system analysis. In this lesson, we will continue our discussion on power system stability. In the last few lessons, we talked about rotor angle stability, in which we discussed how we can analyze the stability of a system for small disturbances, that is, we use small signal analysis, where we use the linearized model of the system. In today's lesson, we will talk about large signal stability, that is, we are going to talk about large disturbances when they take place, how the system responds to that. So, we will start with large signal stability, what we understand here. We will then go into the equal area criterion method for analyzing the stability of a single machine connected to infinite bus system for large disturbance, and we will take some example to clarify this idea, how we use this equal area criteria. Well, once we complete this lesson, you should be able to explain the concept of large signal stability. After that, you should be able to develop the concept of equal area criterion for transient stability. In fact, the large signal stability that we talk about is popularly known in power system literature as transient stability. So, we will interchangeably call them as large signal stability or transient stability. So, develop the concept of equal area criteria for transient stability analysis for single machine infinite bus system, and you would be able to analyze transient stability for single machine infinite bus system using equal area criterion. That is, we will work out some problem on this, and since you would know how to solve this, you should be able to analyze for any other system as well.